Okay, so let me start by thanking the organizers for having me here and allowing me to present this work, which concerns the quantum Hall regime of a bilayer graphene. And in particular, the questions we were interested in is what is the nature of the interactions that stabilize these quantum Hall phases. I'll describe what I mean by this as we go along. So let me begin by acknowledging my collaborators. This is a joint theory and experimental work. The experiments were done in the group of Jun Zhu at Penn State, mostly by Kerr. And the theory was developed by jointly by Efra Chimshani, Ganpathy Murthy, Fertig, and myself. So let me very quickly run through the basics of graphene. I think everyone knows that it's a honeycomb lattice. It has two inequivalent sides, A and B. It's a semi-metal. The valence and conduction bands touch at 2 points, at two inequivalent points, the K and K prime, which are the two valleys. Once you add a magnetic field, the linear dispersion gives way to some Landau levels. The dispersion goes like square root of n. And in particular, there is a very special set of levels at zero energy. Each of these is fourfold degenerate due to the two spins and two valleys. And so if you put the chemical potential in one of these levels such that some of them are occupied, the ground state will be decided by interactions. And this, so one expects some rich quantum Hall ferromagnetism in both the spin and valley space. So what are these interactions that govern the quantum Hall ferromagnetism? The long-range Coulomb interaction is the largest scale of the problem, but it is SU4 symmetric. So it does not decide what is the ground state. Instead, it is decided by the lattice scale corrections, which reduce the symmetry to the actual symmetry of the problem. It's an SU2 in the spin space and a U1 cross Z2 in the valley space. So what is the Z2? This is just a permutation symmetry between the two valleys. What's the U1? Since each of these valleys lives on a different wave vector, and k minus k prime, or 2 times k minus k prime, is not a reciprocal lattice vector. In order to conserve charge, you must conserve both the global charge. In order to have translation invariant interactions, you must conserve charge in each valley individually. This means you must conserve the global charge as well as the relative charge of each valley, and this is the U1 which enters here. In the continuum limit, this can be modeled. The U1 cross Z2 can be modeled phenomenologically through an XXZ Hamiltonian. And for the nu equals 0 phase of monolayer graphene, Haritonov found a phase diagram in terms of the two parameters of this XXZ model. So U perp is the coefficient of the XY term, and the UZ is for the Z term. And what he finds is that either there are magnetically ordered phases, ferromagnet or canted antiferromagnet, or there are charge ordered phases, a bond order or a charge density wave, which are all separated by some first order transitions, except between the canted antiferromagnet and ferromagnet, which is a continuous transition. Each of these is an insulator, except for the ferromagnet, which is a quantum spin Hall insulator. The transport experiments seem to suggest that the ground state is magnetically ordered because when you tune the Zeeman energy by applying an in-plane magnetic field, one finds a transition from an insulating phase where the conductance is 0 to something which has a conductance of almost 2e square over h. On the other hand, recent STM experiments seem to find evidence for Kekule bond order or even charge density wave order. So it seems that there is an experimental puzzle. One doesn't know what is the actual ground state here. And a nice way to reconcile these experiments was proposed recently by Ganpathy and Sumathi and their collaborators, where they suggested that the form of these interactions is modified because of Landau level mixing. And so one of the features of Kharitonov's model was that these XXZ interactions were short ranged. And the reason was that these are believed to come from lattice scale interactions. The lattice constant is much smaller than the magnetic length. So in a continuum model, they would look something like a delta function. In terms of pseudopotentials, it would only be the m equals 0 pseudopotential. So if you relax this condition and allow for higher m pseudopotentials in your interaction, one can find a much more complicated phase diagram. Depending on parameters, you may find some coexistence regions where both bond order and canted antiferromagnet order coexist. This would be one way to reconcile the experiments. Now, the scale of these interactions, this Landau level mixing in monolayer graphene is a constant. It's the ratio of the Coulomb interaction to the cyclotron gap. And depending on your substrate, it can vary from something very small to something large. In freestanding graphene, it can be as large as 2. If you encapsulate the graphene in boron nitride, it can be much smaller. So this motivated us to look for signatures of Landau level mixing in these short range terms in other graphene systems, and in particular in a bilayer graphene. So I'll talk about Bernal bilayer graphene, where you have two of these honeycomb sites. They are arranged, honeycomb layers, they are arranged such that the B site of one layer is on top of the A site of the other layer. Importantly, there is the unit cell has an inversion center, and this inversion symmetry about this point can be broken in a dual gated device by adding a displacement field. If I did not have a magnetic field, then this displacement field would simply open up a gap. But in presence of and this allows you to kind of tune the breaking of the inversion symmetry. If you add a magnetic field, the Landau spectrum in bilayer graphene goes something like this. It is square root of n minus 1. So for very large n, it would go exactly like what you would expect from a parabolic dispersion. However, because of the quadratic band touching, there is a special set of zero energy Landau levels, which are fourfold degenerate because of the spin, the valley, which I will call alpha plus and minus, and also this orbital index, n equals 0 and n equals 1. So due to the nearly eightfold degenerate Landau levels, you can have a much richer set of quantum Hall phases in the range of -4 to +4, which you may be able to tune between by using the displacement field. Another fact is that the Landau level mixing scale in this material goes as 1 over square root of B. And for the samples which June has, it goes as 2.5 by square root of B, which tells you that for low magnetic fields, something like 10 Tesla or lower, this number kappa can be as large as order 1. But for higher magnetic fields, it can be much smaller. So you have this 4-site unit cell. One can write some tight binding Hamiltonian and go to the Landau basis and calculate the Landau levels. I'm not sure that these formulas are very meaningful here, but the point I want you to note is that there is a valley layer locking, in the sense that you see the states belonging to the plus valley, the 0 and the one, they are predominantly localized on one of the layers, on the A side, with a very, very small weight on the Bernal side of the other layer. And it's the opposite for the other valley. The minus is localized on the other layer. This valley layer locking means that the displacement field D, which acts as a potential on the two layers, is really a Wally-Zeeman in the Landau basis. And one can use this to actually, one can check how the Landau levels, Landau spectrum evolves as a function of this electric field, displacement field. And you see something interesting. So at 0D, of course, the plus and the minus are degenerate. There is perfect inversion symmetry. Applying a finite D increases the energy of the states localized on one layer, decreases it for the other layer, but this leads to a crossing between Landau levels of opposite spin, opposite orbital and Wally indices. Now, a fact about a bilayer graphene is that for finite filling factors, these are the ground states are maximally spin polarized. This has been confirmed experimentally. And so in this talk, I will not be concerned with the nu equals 0 phase, only with the finite filling factors. And so I can actually ignore one of the spin sectors and only consider only consider one of the spin sectors here, which is relevant here. So this crossing point should show up as a first order transition for all filling factors between 1 and 3. And this is the data from June's lab. It's a map of a RXX as a function of the displacement field and the filling factor. The dark colors correspond to 0 RXX. So one can see both the integer and the fractional phases. Interestingly, you also see even denominator phases here. So it's a pretty good sample. For each of these, for each of the fractions between 1 and 2 and also between 2 and 3, if you increase, as you increase the displacement field from 0, what you find is that at some point, there is a peak in RXX, signifying there is some kind of first order transition. What you also see is that, okay, and there are some labels here, such as the +0, -0, and so on, which are supposed to indicate which a Landau level is my chemical potential pinned. So for example, if the filling factor was between 1 and 2, it would be pinned to 0 plus below D star and 1 minus above D star. And that's what is indicated here. So how do we know that this ordering is even correct? What you see is that the one indication of this is to look at the even denominator phases. So you see for the 3/2, it only exists above a D star or below D star or below the negative D star, but not in between, which makes sense because we know that the pseudopotentials of the n equals 0 Landau level do not support a quantum Hall state at even denominators, whereas those of n equals 1 do. If you go between filling factors 2 and 3, the situation is reversed. Now you see a 5/2 state between the two D stars, but not above and below, which is again consistent with the ordering we had earlier. And between 3 and 4, there is always a even denominator phase. One thing which you notice is that the D star is a function of the filling factor, even though even when it is within the same chemical Landau level, which is signifying that interactions are having some effect. This is something you would not expect from a single particle picture. However, what is surprising is that this dependence is pretty smooth. It doesn't seem to fluctuate wildly between say 4/3 and 7/5 and 3/2, Whereas we know that the correlation energies that stabilize these phases, they do not evolve so smoothly. So there must be something more systematic going on here. So now we are going to focus between filling factors 1 and 2. And what we notice here is that at 18 Tesla, the slope of D star as a function of the filling factor is negative. If you go to a higher field, such as 28 Tesla, then this changes sign. So here they're plotting only the D star if on the negative side, which had a positive slope here and clearly has a negative slope here. This change of sign at higher fields is also consistent with the previously reported data in a different sample with a different kind of measurement. So this does not seem to be a sample dependent feature, and perhaps we can use it to model our interactions. This plot just summarizes what we have seen so far. This is a D star as a function of the magnetic field. For low fields, the D star for 5/3 is below that of 4/3, whereas there is a crossing point somewhere around 26 Tesla, indicating the change of the sign of the slope. If you look at the D star for nu equals 2, it shows some more features. For instance, there clearly are two peaks, a positive and negative, let's say at 14 or 15 Tesla. But as you reduce the magnetic field, the peaks come together and seem to merge at somewhere around 11 Tesla, which tells you that the critical field has crashed to 0. So now one can ask a question as to what is the nature of the nu equals 2 phase below, let's say 11 Tesla. It is also very curious that they actually do not observe D star for nu equals 2 above something like 19 Tesla. And it's not so clear why. So one can also ask a theoretical question, can we say something about the nature of the D star? Can we say something about the nature of the nu equals 2 phase at very high fields, higher than 19, and also at very low fields? So these are the puzzles that we would like to answer. And we know that this must be an interaction effect. So this is our model. We have two kinds of interactions. There's a screened Coulomb interaction, just a density. And then there are the lattice scale interactions, the XXZ model in the Valley space. So tau here stands for the Valley degree of freedom. The screened interactions take into account screening from the gates, as well as there is some RPA level corrections coming from the negative field Landau levels. The lattice scale interactions, to begin with, we start with just the Kharitonov model, where we assume that these interactions are both short-ranged, as well as independent of the magnetic field, up to an overall scale factor of B, which comes from projection into the Landau levels. If you take this model and you perform a Hartree-Fock analysis, and specifically you want to compare the energies of the states 0 minus, 0 plus, and 0 minus, 1 minus, which are the two phases. Which are the two competing phases according to this picture between filling factors 1 and 2. Then you can get an expression analytic expression for D star, and one can extract an expression for the slope from that. The expression is very complicated, but what one essentially finds from that is that what you can deduce from this expression is that the slope of a D star as a function of nu is always going to be positive or negative, depending on the sign of the Baire interaction for all values of the field. And if you add more interactions to this model, which is allowed in Bilayer graphene because the orbital degree of freedom does not have any symmetry, so you can in principle add an orbital structure to each of these. it doesn't actually change this. So what you really need in order to explain the change of sign of this M star as a function of magnetic field is to introduce some field dependence in the interaction itself. The most natural way to do this is again Landau level mixing, the scale of which is controlled by this parameter kappa. And so here we do it phenomenologically by adding to the constant G naught, a term which looks which has some Gaussian features. And so in particular, these corrections may either be positive or negative. They introduce some explicit B dependence through the kappa. And also the range of these interactions is not set by the lattice constant, but rather by the magnetic length. So here we are going to take this model and ask how large should these corrections be in order to explain the experimental data. So if you try to fit, let's say, just a change of sign of slope at 26 Tesla, then you can do this for any bare value of GZ. There is always some value of GLL of Z within 0 to 1, which with which you can change, you can get this change of sign. This 10% change due to Landau level mixing is actually consistent with some previous calculations. Although those were performed on a different sample, they were performed for a parabolic dispersion. And what the question, so the question asked there was, what is the renormalization of the Coulomb interaction to itself? But even in those cases, it was found that the correction to the short range components can be as large as 10%. So these numbers are not completely implausible. One can also try to fit ask what should be, so can we fit both the constraints, both the change of the sign of the slope, as well as the D star going to 0 for mu equals 2. And so these constraints rule out some parts of the bare terms, but one can in principle still fit the data to this model to the experimental data for over a pretty wide range of the bare terms. What one finds is that both the UZ and the UXY terms must have both attractive and repulsive components in different channels. One of them in the short range channel and one of them in the finite range channel. One can take this model and then go ahead and ask what is the full phase diagram at filling factor 2 as a function of the displacement field and the magnetic field. So focus just on, let's say, the blue line here. The solid line denotes a first order transition between a layer unpolarized phase and a layer polarized phase or a valley polarized phase. Within our model, what we find is that this first order line ends at some magnetic field which depends on the parameters, and then it gives way to a continuous phase transition. In this yellow window, basically the Landau levels of the opposite orbital and opposite valley which were crossing, they hybridize, and a gap opens up, allowing for a continuous transition from, let's say, 0 minus 0 plus to 0 minus 1 plus. Of course, since again k minus k prime is not a reciprocal lattice vector, what this really indicates is that the system is trying to break translation invariance in some way, and the most natural way for it to do so would be to form some kind of a bond ordered phase. So what's really happening in this phase diagram is that at very low values of B, the GZ is becoming negative because kappa is very large, and that negative GZ favors a valley polarized phase, a ferromagnetic phase in the valley space, which allows you to break inversion symmetry spontaneously even at zero displacement field. Whereas at large values of a magnetic field, GZ is positive, and that in addition to the GXY term allows you to have a valley coherent phase. Okay, so one can ask whether this is consistent with the experiments, and if this gap doesn't close across the continuous transition, then one would not expect to see a signature of a first order transition. And indeed, they don't. So this is not a proof, but perhaps this is the reason why they don't. So let me summarize with that. What we did is we looked at some pretty detailed features of the quantum Hall phase diagram of bilayer graphene in a certain filling factor window. We found that in order to explain these, one needs to consider a Landau level mixing corrections to the effective interactions, which introduce both repulsive and attractive components. And a prediction of our model is that there will be some bond ordered phases at high fields for nu equals 2. This model can then be extended, and we can use it to look at phase diagrams for other filling factors. In particular, the most interesting would be multi-component phases such as 2/5 and 2/3, because one can ask whether whether Halperin-like phases are being stabilized close to this first order transition line. One can also ask what is the nature of the even denominator phases at low B, where kappa is large, and think about Landau level mixing in other graphene systems. Thank you.
Thank you very much. Questions for Udit? You have a mic?
Yeah, I have a question that you were showing the Landau level mixing for this bilayer graphene, which I remember is inversely proportional to square root of B.
Yes.
If I ask that if I twist two layers, which is a twisted bilayer graphene, how that will modify with a different angle?
So you mean you want to take twisted bilayer graphene and then add a magnetic field to it? So right. So what you would have to first yeah, okay. So you see, the reason you get something like a square root of B is because in bilayer graphene, you have this quadratic band touching, which gives you, which makes the, so that the cyclotron gap depends linearly on the magnetic field. Then this ratio gets this factor of 1 over square root B. If you take twisted bilayer graphene, and if you go close to the magic angle, I guess you are going to get some flat bands. And then I'm not sure what how the cyclotron energy would scale and things like that. So I'm not sure what this will look at, what this will look like. Yeah.
Okay, other questions? Okay, if not, let's thank Udit and all the speakers of this session.